Hi everyone, in this video we're going to continue with chapter 3. In the last one we saw how the hydrostatic force acts on a horizontal plane. So in this video we're going to look at a vertical plane. Okay, so vertical plane can be anything that is vertical, either a wall like this, or it can be a plane that is fully inside this fluid body. Okay, so for most common application for vertical plane is a wall of a container like this. Okay, so let's take a look at this diagram first. So this is part of a pool, similar to the one you saw in the previous video, but only part of it is taken here. And this is the surface. We have an entire height of the fluid body. And what do we have? We have atmospheric pressure. Atmospheric pressure, there are two parts that are acting on the wall, which is from the outside. Of course, we have atmospheric pressure acting on everything, right? So we have it on this side and we also have it on the inside. Okay, and where there is fluid in the pink area here, there is an additional pressure given by rho GH. So at every point here you have, this is PATM at the surface. As you go deeper, there'll be PATM plus rho GH, and then PATM plus rho GH until the bottom. The difference between the top and the bottom is that the rho GH value is different as you go down this fluid body. Right, the rho GH is of course higher at the bottom. So that is the reason why you have this triangular profile. Also recall your statics. If the load is not evenly distributed, you'll have this profile. It's higher at the bottom. Okay, therefore the lines represent the magnitude. This arrow here or the vectors here, they represent the magnitude. So that's why it is bigger at the bottom or wider at the bottom. Okay. But the atmospheric pressure is not wider at the bottom because this is the same value throughout. So that's why if you just take this portion, in the inside portion is distributed evenly. And then the increase starts at the surface because this is where the water starts to exert pressure. Over here at the top, there's no water. So it starts here, increasing at the bottom. All right. So atmospheric pressure can be neglected when it acts on both sides of the surface. So to ease your calculation, because atmospheric pressure here is acting on the surface at both sides and in opposite direction. Therefore, we can simplify this diagram and turn it into this. So it looks much cleaner, right? So this is the same. You still have rho GH, except that you have cancelled out the PATM. It's not because the PATM is not included, but because it is acting on both sides. So actually the PATM cancels itself. Okay, you're pushing from this side and then you're pushing from this other side as well, so it cancels each other. Okay, so we're left with rho GH. What we want to do in this case for vertical plane is we want to find two things. Okay, commonly what you have to find are, the first one is the resultant force. So remember, resultant force equals to P times A. Yeah, so the resultant force here is a little bit special because do you know where it is? Is it at the center? Okay, if you remember your statics, you should know that it's not acting at the center anymore, unlike horizontal plane. So this is what we want to determine. And the location of the resultant force, where is this CP? We call it center of pressure. This is the location where FR is acting on, which is C. So now let's figure out the equations that we need. So from the previous slide, we have FR equals to PA. Okay, here is a little bit different. I'm writing it as PC. So FR again is resultant force. PC is the pressure on the centroid. Okay, centroid simply means the center of the geometry of the plane. So it's a vertical plane, whatever shape it is, this is the pressure acting on the center. In other words, is the average pressure. Okay, and A of course is the area of the surface. So this is the diagram from the previous slide. Okay, we're going to work it out based on this. What you need to know. A is the area of the plane surface. So obviously you don't see the area here. You're looking at it from this view. So if you know the shape of the wall, which typically is a rectangular wall, or sometimes in some cases you have a vertical plane or a trapezoid. The area depends on the shape. Yeah. Next we have point O, which is the intersection between the plane and the free surface. So this is the plane. The wall here is the plane, and this is the free surface. Where do they intersect? At this point, right? So that's your point O. Next, we have the centroid or C. Remember here, C? So the centroid of the plane, which is also the center of area, depends on the plane shape. So if this is a rectangular wall, then the center is at the center of the rectangle. So I'm just going to put the C here somewhere in between the top and the bottom to show that it's at the center. Next, we have center of pressure, CP. Okay, center of pressure is always lower than C. Okay, I'm going to put it somewhere here because it's always lower than C. I hope you are asking yourself, why is center of pressure here? Okay, and why is it not at the center? Okay, Fr is the magnitude of the resultant force, and it's always perpendicular to the plane. So the plane is vertical, so of course Fr is horizontal, and it is acting at Cp, exactly at Cp. Okay, still haven't answered why it's lower than C, right? So Fr is acting at Cp. Hc is the vertical depth of C. So vertical depth meaning from the top, from the free surface to point C, that is Hc, height of point C, that's what it means. And then we also have HP, which is the vertical depth of Cp, which is of course here. Okay, so now the unanswered question is, where is the Cp? Where should it be? Why is it there? Okay, and how do we get the value of the height? How do we get this arrow? HP. Okay, the answer is you can solve it using this equation. HP is a function of, we have HC, which is easily determined. We have I naught here, which is moment of inertia. If you remember your statics, moment of inertia, I'm going to go to this next. HC again is the same thing here, and A is simply the area, which you already have. Okay, so why the center of pressure is here is because of this unevenly distributed load. Okay, so because of this triangle, you know that the center of a triangle is actually about 1/3 from the bottom. Okay, that is the center of a triangle. Therefore, the center of this resultant force is not going to act at the center of the plane. It's going to act at the center of this load here, right? So that's why it is always lower than the center of the plane, because naturally we have higher pressure at the bottom, therefore higher force acting at the bottom. So this is the reason. And to calculate what is the value of HP, where is the CP, you can use this equation. Okay. Okay, so just now we have this equation to determine the position of the CP. And to do that, you need HC and E, and also this moment of inertia. Moment of inertia is also called second moment of area. Depends on what book or reference material you are using. So let's clarify C and CP. C is simply this location. Okay, for different shapes, you have different C. And to know where they are, you can just refer to the dimension here. Okay, I think for all these three shapes at the top, they are all at the center. But for these three, they are different. Okay, you've seen this in your statics. Now let's say the C here, the center is of course halfway from the top. So let's say our wall just now is rectangular, so the C will be halfway from the top. Okay, but the moment of inertia cannot be pointed out here. You have to calculate it. So let's take for example, this is the equation. We want to take I naught is also equal to this Ixx. Yeah. So that will be based on this, based on the square, it's AB cubed over 12. Be careful with this. A is the bottom side and B is the height. A is the width and B is the height. Cubed divided by 12. So that will get you I naught. So where do you get A and B? Of course, from the shape of the geometry. It will be given in the question. How wide the wall is, how tall the wall is, etc. Okay, so I hope that's clear. Now we can look at other shapes. So you can go through this. I've also uploaded this as PowerPoint form. So you have a trapezoid here, which is very complicated. In this case, the moment of inertia is here. Okay, so you have to really uh, make sure that you get the right A, B, and H. Where is A? A is the short side, B is the longer side, and H is height. Make sure you get this right. And more shapes. And I think, yeah, the next one is an example. So we have a plane surface, which is circular. Okay, this time we have a circular plane with a diameter of 2 meters. The diameter is 2 meters. If it is vertical and the top edge is 0.5 below the water surface, find the magnitude of the force on one side and the depth of the CP. So like I said, you always have to determine FR and location of CP. Okay, the difference between this question and the explanation diagram before is that in this question, the plane is underwater, yes, and it has some depth of fluid level above it. So it doesn't reach the free surface. Okay, that's the difference. So we're going to see how that changes things. So to find FR, we have this equation, FR equals to PCA. And of course, PC can be expanded to rho G HCA. So you see the C is kept here at the H. So HC is the height from the free surface to the centroid or the center of the geometry. So the height, the HP can be calculated from this equation, and the HC, let's solve for this. HC is from the top to the center. Okay, so the common mistake here is that you only take the top of the plane until the center, which is going to be wrong. You have to take it from the top of the fluid body, which is the free surface. So radius 1 meter plus another 0.5. So you get HC is 1.5. Next, you can just put all these values into the equation here. So rho G HC area, okay, which is pi r squared. Solving, you get 46.2 kilonewtons. Now the CP, you can just use this equation because remember, HP is the height of the CP from the free surface. Okay, so I repeat that HP is the height of the CP point from the free surface. So that will be, you just substitute the values. You have HP equals to HC calculated here. I naught. Now you can pause and you can Google for the moment of inertia of a circle. You'll find that it is this pi r to the power of 4 over 4 divided by, this is HC again, 1.5 times area, which is pi r squared. and then you will get the answer. Okay, that's basically it for vertical plane.